Today we're going to look at the derivative as a function. So what is the derivative? The derivative is just another word for the slope of the tangent or the instantaneous rate of change. The definition of the derivative is given by the following formula. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. And all we're saying is, if you take this secant line here between the points P and Q, we're going to take this Q value and we're going to bring it very close to the P value. So this h is approaching 0 of delta y over delta x. And our delta y is the f of x plus h minus f of x. And our delta x is the x plus h minus x. And x plus h minus x is just equal to h. And again, we have this note provided the limit exists. And we're going to look at that today. Now we have some other notation. You might see f prime of x written as dy over dx. So again, all this is here is the derivative is just the slope of a tangent. So it's going to be our calculus notation to state that we're looking for the equation for the slope of the tangent of a curve for all x. So again, the formula will determine the derivative, slope of the tangent, instantaneous rate of change. So these three terms are interchangeable. So for example 1, we're going to look for the derivative of the root of x. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And all that is the limit as h approaches 0. So if we sub an x plus h into our root function, we get root of x plus h minus root of x all over h. Remember, for an example like this, if we were to sub in h equals 0 at the moment, we're going to get 0 over 0. So that's called our indeterminate form. So that means we need to try some method to see if the derivative exists. And for this example, we're going to multiply by a conjugate. So we have root x plus h plus root x divided by root x plus h plus root x. So now we're going to distribute the numerator and just multiply or leave the denominator. So we have the limit as h approaches 0. So we're going to get root x plus h times root x plus h, which is just x plus h. Then we're going to get root x times root x plus h minus root x times root x plus h, so that equals 0. And then finally we're going to get minus root x times root x, which is equal to x. In this case, minus x. Our denominator is h times root x plus h plus root x. And you notice in the numerator, we're just left with the factor of h. So we have the limit as h approaches 0 of h over h times root x plus h plus root x. We can cancel out our h's. And we're left with the limit as h approaches 0 of 1 over root x plus h plus root x. Now we can sub in h equals 0 and determine the derivative for this function. So I have 1 over root x times root x, so that's 1 over 2 root x. And that is the derivative for the root of x. Now we can find the slope of the tangent line for any x value where this derivative is defined. So where is this derivative defined? Well, it's defined for all x, except x cannot equal 0. So there is the domain for our derivative. Alright, example 2. Determine the equation of the tangent line of y equals x to the fourth plus x cubed minus 3 at x equals 1. So in this case, we're not going to use our f prime. We're going to use dy over dx since we have y representing our function. So this is the limit as h goes to 0 of f of x plus h minus f of x all over h. So let's take a look at the numerator. So we have f of x plus h minus f of x, and that's equal to x plus h to the fourth plus x plus h cubed minus 3, and then minus f of x, which is x to the fourth, plus x cubed minus 3. Now for this one, to expand it quickly, we should use Pascal's triangle. Remember, Pascal's triangle looks something like this. Notice we need up to row number 4 to expand our x plus h to the fourth. So starting with row number 4, notice our first coefficient is 1, so we're going to get x to the power of 4. Our next coefficient is 4, so it's 4. We bring down the exponent of x, so that's x cubed, and then we bring up our exponent of h, so that's x cubed h. Then plus 6, x squared h squared, again plus 4, and that's going to be x h cubed, and then h to the fourth is the expansion. So this is the expansion of all of this. And let's do the cube function. So that's going to be plus, so now we're going to go to this row here, row 3, that's x cubed, and then we're going to take the coefficient 3, bring down the x, bring up the h, and keep on following that pattern. And then we have our minus 3, and then we have the subtraction of x to the fourth minus x cubed plus 3. Again, this here is all of this here. Now you know you've done this right if all the terms without an h cancel. So the x to the fourths cancel, the x cubes cancel, and the 3's cancel. And we're left with terms that only have an h, which is important because we need a factor of h to cancel out the h in the denominator. So let's add that to our limit. So this is equal to the limit as h approaches 0 of 4x cubed h plus 6x squared h squared plus 4x h cubed plus h to the fourth plus 3x squared h plus 3x h squared plus h cubed, and that is all over h. So this is equal to the limit as h approaches 0. Notice there's a common factor of h in each of these terms, so I can take out h here, and h here, and h here, one here, one here, and one here. And that'll cancel this h here, and we're left with 4x cubed plus 6x squared h plus 4x h squared plus h cubed plus 3x squared plus 3x h plus h squared. Which looks like a big function, but now when we sub in h equals 0, that'll go to 0, that'll go to 0, that will go to 0, that, and that. And we're left with this derivative dy over dx is equal to 4x cubed plus 3x squared. All right, so we want the equation of the tangent line, so we want that whole equation at x equals 1. So our first step is to determine the slope. So the slope of the tangent line is equivalent to dy over dx, and we want it evaluated at x equals 1. If we sub 1 into the equation above, we get that the slope is 7. So now we have the slope. Next we need a point. Well, we know the point of tangency is at x equals 1. If we sub 1 into our original function, we get 1 plus 1 minus 3, so it gives us negative 1. So there's our point of tangency. And then finally we have that y is equal to 7x plus b. We sub in our point, so negative 1 equals 7 plus b, and b is equal to negative 8. So therefore, the equation of the tangent line at x equals 1 is y equals 7x minus 8. So again, two key points. This was the slope of the tangent, and this was the point of tangency at x equals 1. And this was determined by subbing it into our equation for y. So that was y equals x to the fourth plus x cubed minus 3. Example number 3. Determine where the slope of the tangent for y equals 1 over x plus 1 is equal to negative 9. So this method will help us find an equation for all the tangents, which is great because then we can solve for where it equals negative 9. So let's go through our steps. Again, we're given an equation in terms of y, so we're going to say dy over dx is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So f of x plus h minus f of x, that's 1 over x plus h plus 1 minus 1 over x plus 1. So we want a common denominator, so I'm going to get x plus 1 minus x plus h plus 1 all over x plus h plus 1 times x plus 1. We see that the x disappears, the 1 disappears, and we're left with negative h over x plus h plus 1 over x plus 1. So let's sub that into our formula for the slopes. So this is the limit as h approaches 0 of negative h over x plus h plus 1 times x plus 1, and then divided by h, or if we divide by h, we're going to multiply by 1 over h. It's perfect because the h's now cancel, and we're left with the limit as h approaches 0 of negative 1 over x plus h plus 1 times x plus 1. Now that we've canceled the h, we can now sub in our 0, and we're going to end up with negative 1 over x plus 1 all squared. So this is the slope of the tangents for the function given above for any x value. Except we do have a restriction. In this case, x can be any real number. However, we don't have the slope of any tangent at x equals negative 1. So we want to determine at what points does the slope equal negative 9. So if dy over dx is equal to negative 9, then all we need to do is solve the following equation. Negative 9 is equal to negative 1 over x plus 1 squared. So let's solve for x. First thing I'm going to do is multiply both sides by x plus 1 squared. So I get 9x plus 1 squared, and I divided both sides by negative 1. Then we're going to expand and simplify the left side. So if you want to try that, you should end up with 9x squared plus 18x plus 9 equals 1. Let's move the 1 to the left side. So we end up with 9x squared plus 18x plus 8 equals 0. So now we need to factor and solve. So let's check if this is factorable. So we get that b squared minus 4ac. If you check that value, you end up with 36. So this tells me that this is factorable and it has 2 roots. So if I want to factor this expression, I end up with 3x plus 2 times 3x plus 4. And that equals 0. So we get that x is equal to negative 2/3 and x is equal to negative 4/3. So this is where the slope of the tangent for the function is equal to negative 9. And if you're curious as to what that looks like, let's say here is our graph of our function. So we know it has a vertical asymptote at negative 1. And what we're saying is we have a slope of a tangent equal to negative 9. Let's say somewhere here and somewhere here. So those would be your two x values, negative 2/3 and negative 4/3. So let's talk about when does the derivative not exist. A function f is said to be differentiable at x equals a if f prime of a exists. At points where it's not differentiable, we say the derivative does not exist. And here are 3 cases that you will run into. The first one, you could end up with a cusp. So if I tried to draw the slope of a tangent line here, notice I could draw one, but I could also draw different variations of it. An example of a function that develops a cusp is the following. The next one is that you end up with a vertical tangent. So look at here. If I tried to draw the slope of a tangent, it would be a vertical slope. So it would be undefined. And that one is given by this function here. And the third case is where the function is discontinuous. So we talked about discontinuity the other day. Wherever the function is discontinuous, I can't really draw the slope of a tangent. So if there's a discontinuity, there is no tangent line at that point. So let's take a look at an example and explain why the absolute value function is not differentiable at x equals 0. So first of all, let's look at it graphically. So here is our absolute value function. And you can see at x equals 0, we have a corner. So we can see that as you approach from the left of 0, all the slopes appear to be negative. Whereas as x is just above 0, or coming from the right of x equals 0, we see that the slopes are all positive. And in this example, the graph has a corner at 0, 0, which prevents us from drawing a unique tangent line. We can draw multiple tangent lines here. So there's one that touches once, there's another, and so on. But let's now talk about this algebraically. Let's use the definition of our derivative. So let's say we want to find f prime at 0. And recall the other day, that's the limit as h approaches 0 of f of 0 plus h minus f at 0 all over h. So that's the limit as h approaches 0. Well, notice I have f of 0 plus h, so that's just f of h, and f at 0 for the absolute value function is just 0 all over h. So that's equal to the limit as h approaches 0. Well, what is f of h? Well, that's just the absolute value function, so that's the absolute value of h all over h. So we need to evaluate this limit. So next we're going to consider the one-sided limit. So as the limit of h approaches 0 from the left and h approaches 0 from the right. So let's look at the left. So the limit as h approaches 0 from the left of the absolute value of h over h. Well, that's the same thing as finding the limit as h approaches 0 from the left. Since 0 from the left is always going to be a negative number, I can just rewrite the absolute value as negative h, because now if I put the negative number into there, it becomes a positive number. So I get the limit as h approaches 0 from the left of negative h over h, which is equal to the limit as h approaches 0 from the left of negative 1. Now if I sub in h equals 0, I get that the slope of a tangent is equal to negative 1 as you approach 0 from the left. Now let's take 0 from the right. So it's the limit as h approaches 0 from the right of the absolute value of h over h. That's equal to the limit as h approaches 0 from the right. And in this case, since it's positive, I can just write this as h over h. And that's equal to the limit as h approaches 0 from the right of 1, which tells us that's equal to 1. Well, what do you notice about the left and right hand limits? They're not the same. And since they're not the same, that means that this limit here does not exist. And remember, this thing here is equal to our derivative, f prime of x, or in this case, f prime at 0. And it does not exist at x equals 0. So try the following questions. You notice for question 16, I say to see example 4. That is the example that we just completed. Good luck.